In relating forces to motion, in terms of an equation, we're going to use Newton's second law as a reminder that tells us that the net force on an object is equal to the mass of the object times the acceleration. Essentially, the acceleration an object experiences is directly related to the net force, meaning the summation, the addition of all the force vectors acting on the object, and that acceleration is inversely related to the mass of the object. So, to accurately use Newton's second law, we need to be able to recognize and represent every single force acting on an object. So to help us and aid us in problems, we use and draw what's called a free body diagram. We often abbreviate this as FBD just to talk about it and make it simpler to write out. So free body diagram means vectors representing all forces, so each vector will represent a given force. And then these are all labeled. So, for example, let's say I was pushing a box along the floor. And I wanted to describe just pictorially and in terms of Newton's second law, just conceptually, how the forces would apply to this box, essentially. So in general, I have a box, I know I'm pushing it, so it's moving along the floor. That's my rough sketch. My free body diagram, right now, we are using what's called the particle model. If you remember back to chapter 1, we used dots to represent our object in a motion diagram, and we could represent whether the object was speeding up or slowing down. We're still using that particle model right now. And until we start rotation in chapter 12, we will continue to do so. So this little dot that I have drawn represents my box. It represents the object of interest that I'm talking about. On this dot, I want to represent all of the forces. So I'm going to draw a vector, an arrow, representing each of the forces acting on the box. So I've already mentioned that I'm pushing it. I like to draw all my vectors starting on the dot. So my push, I'm just going to represent by a vector pointing to the right. In order for the box to move to the right, I have to be pushing to the right. But that's not the only force. Remember, forces fall in the categories of contact or field forces. So field force, of course, we always have the force of gravity. The box would be experiencing that force of gravity straight downwards towards the center of the earth. Whether we label it as F sub g or just go ahead and say mg in the first place, that's fine. Either way, but we need to label that vector so that we know what that vector represents. Which force does it represent? Okay, that's the only field force. Any other forces the box might be experiencing fall into this contact category. The pushing force that I've already drawn is a contact force. It's because my hands are on the box and I personally am pushing the box. But the box is also in contact with the floor. Well, the floor is a surface, so there has to be a normal force upwards from the floor. The floor is pushing up on the box. Now, realistically, if I had a box on my actual floor in my house, it's not a nice, beautifully, perfectly smooth surface. So I would say there's some friction. I know that friction makes it a little bit harder to push. That friction would be opposing my push. So I would draw that pointing to the left. Now, friction is a contact force as well because of the box sliding on the surface of the floor. We're going to use a lowercase f. This represents, in this case, what we call kinetic friction force. We'll be talking about static friction as well. We will use a lowercase f to represent that type of friction. So it's common to use this lowercase f just in general to represent any type of friction. We will often put a subscript. So in this case, a subscript of K to represent this kinetic friction. What we mean by kinetic friction is the friction as the object slides on the surface. So any object sliding on a surface, when we talk about the friction in that case, we talk about kinetic. So right now, this particular video, I want to focus on drawing these free body diagrams for a number of situations. And then I also want to relate that back conceptually to Newton's second law. So for example here, in this free body diagram I've just drawn, I've tried to draw the normal force upwards the same length as the force of gravity downwards. I don't know if I did that perfectly well, but the reason why, conceptually, I know this box is not accelerating in the y direction. If it had an acceleration in the y direction, that means its velocity would have to be changing up or down in that y direction. So the box would have to be lifting up into the air like a rocket or sinking down into the ground like quicksand. I know the box, even though it's moving just horizontally in the x direction along the floor. We're essentially recognizing that the acceleration in the y direction has to be 0. But going back to Newton's second law, we know the net force over mass is what determines acceleration. If I'm talking specifically about the acceleration in the y direction, then I'm relating that directly to the net force in the y direction. When I come back to this free body diagram, so this picture with the dot and all these forces is this free body diagram that I have mentioned. So the vectors representing each individual force, those vectors are labeled with what force they are representing. In my picture, the only forces I've drawn in the y direction, the only forces we have in the y direction are the normal force and the force of gravity. So if I know there's no acceleration in the y direction, then the forces, these y components, forces in the y direction need to add up to be 0. So since I have just the normal force up and the force of gravity down, they have to be equal. So essentially, we're saying the net force, specifically in the y direction, accounting for those directions, we would have the normal force up, meaning the positive direction, adding that to the force of gravity, mg, downwards. Those would have to add up to equal 0. Writing this a little more clearly, I would say n minus mg is 0, which in turn leads me to n equals mg. Now, just taking a step back and thinking through that conceptually, it's totally great to go ahead and jump to this point of saying n equals mg, which is what I did initially. That came from the practice that I have because I've looked at these free body diagrams. I've used F equals ma for so long. So if you are not yet to that point, which is totally fine, I'm going to walk through this process of talking about acceleration, relating that to net force, to come up with these relationships between the forces. So when we say n equals mg, we're just saying the floor has to push up on this box as hard as the force of gravity is pulling downwards. That's what that says. That's what that means. And we get to that point by reasoning through Newton's second law. Now, the second situation here, though, the box is moving to the right. The way I have drawn my free body diagram, so going off my free body diagram, for the x direction specifically, I have drawn, I'm going to call the push just P. I have drawn this pushing force to the right bigger than the friction to the left. So to account for the forces, the net force in the x direction specifically will be the positive P, meaning the pushing force to the right, minus the friction kinetic. Again, minus, we're saying that's to the left. So similar to the first section that we've already covered, where we talked about direction all the time, plus for right, minus for left, that still holds true now for the same reason. We're accounting for the direction using these positive and negative signs. When I look in my free body diagram, that pushing force to the right, the friction force to the left, those are the only two forces that have components in the x direction. So this right here, P pushing minus the kinetic friction, is the net force. But according to Newton's second law, the net force must equal the mass of the object times the acceleration of this object in that x direction, because we're looking at the forces in the x direction. Ultimately, we're saying the acceleration, just the horizontal component, the x component, this acceleration is determined based off of how much bigger the pushing force is than the friction force divided by the mass. So again, in my picture, I've drawn the pushing force, P, that long. When I subtract friction here, the result, where I started the first vector to where I ended the last vector, This represents the net force. Oh, I'm doing specifically the x direction, so I can just put my subscript of x. The difference between those vectors represents that net force in the x direction, which in turn, that net force determines how much acceleration there is when we divide by mass. So that net force being to the right divided by the mass tells us that the acceleration of the box will be to the right. So if the net force points to the right, meaning the positive direction, the acceleration also points right. It will be in the positive direction. So this box is not only moving to the right, it's going to be speeding up, going faster and faster to the right. Because remember, if the velocity of an object and its acceleration are in the same direction, the object speeds up. And so this is how we end up relating forces to motion in general. The forces directly determine the acceleration, and then we can go back using our knowledge from the previous section to relate that to speeding up or slowing down. So this takes a little practice. I want to talk about another example, and I actually will go through a number of examples of recognizing forces, because this is the first step of solving any problem in this section. The free body diagram is so important that I'm going to require that on every single problem on your test. So I highly recommend you practice drawing the free body diagram, labeling all the forces, setting up the equations as I am showing you, and I will continue showing you so that you are getting in this good practice. This practice will help you in statics, it will help you in dynamics if you're going down the civil engineering or mechanical engineering or physics pathways. It will help you in other areas as well, but the most immediate help is in that regard. Let me walk through one more example here. Let's say we have a box, but it's sitting on like a slide. Or let's actually say it's not a box. The slides in the playgrounds nowadays, that plastic surface, is sometimes not very slippery. Let's say this is a child sitting on a slide. They got stuck, or they stopped themselves. So a child, of course, doesn't look like a box, but I've already drawn the box. Sitting at rest on a slide. And for simplicity's sake, we'll say that this slide is just a nice smooth slope at some angle theta. Now again, right now we're not going to be solving for answers. Right now we're just practicing recognizing forces, drawing those free body diagrams and relating those forces to acceleration. So no numbers involved yet. The first step in any of these problems is to identify the forces and draw that free body diagram. But we do need to know something about what the object, so in this case, a child, what that object is doing. So my child is sitting at rest on the slide. Now, whether we analyze and think about what that means for acceleration first or forces first doesn't really matter. Let's go ahead and talk about forces. So I want us all to get in the habit of drawing the free body diagram. So again, my child is going to be a dot. Every object we talk about in this section will be a dot. I know there's a force of gravity. That's our field force. There's always the force of gravity acting on our object. Because the earth pulls all of us, it pulls everything towards the center of the earth. All right, so that's one. That's our field force. The rest of our forces will be contact. So we have to think about what this child is in contact with. The child is in contact with the slide. They are sitting on the slide, just sitting there. Well, this slide is a surface. Now again, that normal force has to be perpendicular to the surface. So I would label my normal force here. It has to be to the left and upwards as far as my picture is concerned, simply because of how the slope is oriented. There has to be a 90-degree angle between the surface and that normal force. And so that's why I draw that normal force up at an angle. The other type of force the slide can exert on the child is friction. Now, in this case, the child's just sitting there. They're going to stay sitting there. They're not going to slide down. That's what I'm trying to get at right here. So let's just assume in this case, this child is not going to slide. Well, in order to not slide, I know if there was no friction at all, that ideal situation we talked about in chapter 2, that component of gravity would cause the child in this case to have a component of acceleration down the slope. But in this case, if the child's not sliding, then there has to be a force that's counteracting what gravity's trying to do. There has to be a friction force opposing the motion that the child would do if there was no friction. So I know the child would slide down the slide if there was no friction. That means there must be some sort of friction pointing up the slide. In terms of not allowing the child to slide, to stay there, we call this static friction. So we'll still use a lowercase f to represent friction in general. The term static friction means not sliding. Technically, it doesn't mean not moving at all per se. In this case, it does. But the general definition of static friction is that the object is not sliding at all. So here is our free body diagram for this child sitting at rest on a slide. This free body diagram is essential when we actually get to setting up equations. And our equations will all boil down to Newton's second law. Whether we write that as the acceleration of the object is determined by the net force divided by mass, or writing that as the net force is equal to mass times acceleration, it's the same equation. We can set it up either way. We mean the same thing. So to relate this free body diagram, we have accounted for all the forces. To relate that now to what's happening and to acceleration, we want to think about the motion. So for this specific problem, the child sitting at rest, they're not going to slide down the slide. That means there's no acceleration in any direction at all. There's no acceleration horizontally. There's no acceleration vertically. There's no acceleration down the slope. So that means the net force overall has to add up to be 0. When it relates to solving problems on a slope, we are always going to rotate or tilt our axes. meaning we're going to make our x-axis along the slope and y-axis perpendicular to the slope. We can make pointing up the slope or down the slope positive. If you remember from chapter 2, when we were talking about linear motion on a slope with no friction, we said the acceleration would be plus or minus g sine theta. That plus or minus was there to remind us that we had to choose our direction along the slope, whether we wanted up the slope to be positive or down the slope. That's up to us as we solve a problem. So for example, if I call down the slope positive, then I would use the positive here if there were no friction. Okay, this was a special case. So we're not going to jump to using this g sine theta, but what we are going to do is I'm going to come up to our free body diagram we had. By rotating the axis, that puts the static friction force along this new x-axis, and it puts the normal force along this new y-axis. It turns out anytime we have an object either at rest on a slope or moving on a slope, we're always going to rotate the axes. You don't have to, but it simplifies the algebra immensely if we do. So just general rule, make note of that. We will be doing examples as well, and I'll remind you of that when we do those examples. When we rotate the axis, remember this angle up in here between gravity pointing straight down to the center of the Earth and the new y-axis is the same as the theta for the incline or slope. Meaning we can write this as x and y components. Let me move my mg to this side. So mg represents the actual vector. This vector will have x and y components. An x component here, because that's what's parallel to the x-axis. A y component here, because that's what's along the y-axis. The x and y components need to meet at a right angle, 90 degrees. So this y side ends up having a magnitude of mg cosine theta because it's adjacent to that angle. The x side ends up being mg sine theta. So if we go back and remind ourselves that in this specific situation, this child is at rest, they are not going to slide, that means they can have no acceleration. That means the net force has to be 0. F net is 0. That has to be true for both the x and y direction. So if we were to look at the x direction specifically, meaning along the incline, I know we have mg sine theta. We have this component of gravity pointing down the incline, which we're making positive. And then we have this friction force in the up the incline direction, so the opposite direction. So this represents the net force in this tilted axis in what we're calling our x direction. But because this child is not going to slide, this net force has to be 0. Which means that mg sine theta in this case needs to equal the static friction force. You may have noticed that from the beginning, just knowing there's no acceleration, you may very well have noticed that this down the slope component needs to cancel out or balance out this up the slope friction. That's what this says. The component of gravity pointing down the slope has to equal the friction force pointing up the slope to keep this child at rest. This is all boiling down from Newton's second law, knowing there's no acceleration, relating the forces in that specific direction. So that gives us our relationship between the force of static friction and the component of gravity. If we think about the y direction, coming back to our free body diagram, we have the normal force pointing in that y direction, but we have this component of gravity pointing in the negative y direction. Again, since there's no acceleration, we could totally jump to saying the normal force needs to equal mg cosine theta. Those y components of force need to balance out, because if they don't balance out, there's going to be an acceleration in that direction. But since we know there's no acceleration in that direction, they have to balance out. The reasoning through, if you want to do so in terms of net force, we would say the normal force in the positive y direction minus the component of gravity in the negative y direction. This would represent our net force in the y direction. That would have to equal, well, 0, because there's no acceleration in the y direction. So everything we do in this section is going to relate to understanding the acceleration. Is the object at rest? Is it going to stay at rest? Is it going to speed up, slow down? And relating that acceleration to the net forces. This section is the first time we really jump into this mathematical modeling. Our base equation is right here, Newton's second law. Every single problem we solve, we need to write out what we mean by net force so that we can come up with these relationships between these individual forces. And I apologize for the squeaky toys. Apparently it's time to play. All right, so I am going to do a few more videos looking at examples of drawing the free body diagrams and relating that to the motion. Having a conceptual understanding and the ability to draw these diagrams is absolutely essential to solving any problem. So we don't have just a plug and chug situation here. That's very rare in this section. So again, please go through the following examples so that you are getting a good feel of the free body diagrams and relating that to the motion.